Hello everyone. This video corresponds to section 5.5 from Math in Our World. We have already started this section and talked about the real number system as well as classifying real numbers into various subsets. So in this video what I'd like to do is review classifying real numbers and then begin to talk about the properties of the real number system. Here's a review of how to classify real numbers. This is a chart from the textbook, and you can see that we have different subsets which are sort of nested inside this larger set of real numbers. Alright, so notice that the real numbers can be divided between either rational or irrational numbers. Alright, and so what we can say is that the real number system, or the real numbers, is composed of the rational numbers, and there's your symbol Q for quotient, and then if we union that with the irrational numbers, then that makes up the set of real numbers. Right? So every real number is either rational or irrational. Then we have irrational numbers. We don't really go into more details with classifying those, but rational numbers can be broken down into several smaller sets. Right? So remember that rational numbers can either just be rational or they can also be an integer. And then some integers are whole numbers and some whole numbers are natural numbers. Alright, rational numbers are fractions where the numerator and denominator are integers. A and B are integers. Okay, so here's a quick review. Try these out, see if you can classify each number according to its type. So list all of those subsets to which it belongs. Okay, starting with 0. 0 is, let's see, okay, alright, so our choice is natural, whole, integer, rational, real, irrational, and then if it's none of those things it would be basically not real or none. Alright, so 0 is a whole number. It's not natural. It's an integer. And then once you've picked kind of the most specific set, like whole numbers, it automatically falls into all of those larger categories. All right, so this is whole, integer, rational, and real. Square root of 15, that's irrational. And then that also makes it a real number. Negative 3/4, it's not whole, it's not natural, it's not an integer, but it is rational, and it is real. Okay, 0.86, where the 6 is repeating. Again, this is rational and real. Square root 25, this is a trick. That equals 5, so this one is natural, whole, natural, whole, integer, rational, and real. Pi over 3. This is a fraction, so it's tempting to say that this is rational, but remember that the numerator and denominator both have to be integers, and pi is not an integer. So this is irrational. And also real. Alright, and then the fraction 4 over 0, it is a fraction of integers, but it's not rational because the denominator is 0. So that was another one of those requirements, that the denominator not be 0. This one is not real, and so it wouldn't belong to any of the other subsets of the real numbers. Alright, let's start talking about the properties of real numbers. A property is a fact that is always true regardless of the specific numbers chosen. So these are all things that we've proved deductively to be true for the real number system, and then what we can do is apply and use them as long as we're working with real numbers. These are basically the reasons that we use to explain why all of the different operations and arithmetic that we do with real numbers why all of that works. Right? So for example, when you have something like 1/2 equals x over 4, and you may remember that one thing we can do to solve for x is to cross multiply. Well, we have a lot of sort of operations like that, like cross multiply. They're pseudo operations. They're not addition, subtraction, division, or multiplication, but we can explain these in terms of those properties, in terms of those operations, and using these properties. Okay, here's the first one, the closure property. This one states that for any two real numbers a and b, the sum a plus b is a real number, and the product a times b is also a real number. Okay, so if you add or multiply any two real numbers, your answer is guaranteed to be a real number. We say the real numbers are closed under addition and multiplication. Okay, so under means using that operation. All right, so if I had 2 plus 6.245 without even doing that addition, since I know that 2 and 6 are real numbers, I know that the answer will also be a real number. All right, how about subtraction? Are the real numbers closed under subtraction? So let's think about, some common subtraction problems. We could do 6 minus 2, pi minus 4, 0 minus 1/2, square root 15, or square root 12 minus square root 3. Okay, and if you check all of these on a calculator, type all of these in and you will get an answer. Some of these will be decimals, but if your calculator can display the answer and if it doesn't say error or undefined, then that means that the answer is a real number. So we haven't proved this deductively, but inductively, looking at a number of examples, you kind of get the sense that the real numbers are closed under subtraction. When you subtract two real numbers, your answer is always real. All right, how about division? Okay, so we could do 6 divided by 2, pi over 3, square root 12 divided by 4. Okay, and I am using the fraction bar to mean division, but it's the same thing if you write this out horizontally with the division symbol. Okay, same thing if you type all of those in your calculator, those all give you real answers. All right, so inductively, maybe you think that the real numbers are closed under division, and there actually is one counterexample. So the real numbers are not closed under division, and maybe you've thought of this already, but what about something like 5 divided by 0? Well, that's not real. All right, so what we've done is we've taken two real numbers, 5 and 0, we've divided them. Our answer is not real, so that means that this set is not closed under division. Right? You can think of closure as kind of like a room with a closed door. All right, here's the door, and we have all of these real numbers inside, 5, 0, 1/2, etc. And if you can combine all of these numbers, 5 and 0, 0 and 1/2, and if the answer does not leave the room, then your set is closed. It's like this door is closed and it can't get out. But if you can get an answer that's outside the room of real numbers, like 5 divided by 0, then the set is not closed. Okay, let's try some other examples. Make a conjecture about whether or not the following sets are closed under addition, subtraction, multiplication, and division. So these sets are not the set of real numbers, so we don't know for sure anything about these. We have to check and decide whether or not they're closed. If you think the set is closed, explain. If you think it's not closed, give a counterexample. So for instance, the one we just did, 5 divided by 0, that's a counterexample to show that the real numbers are not closed under division. Okay, how about the natural numbers? All right, so we'll go through with addition, subtraction, multiplication, and division, and we'll check each one. Okay, so natural numbers, think about adding things like 2 plus 3, 1 plus 12, 23 plus 156. All right, and inductively, it seems like we always get a natural number. This is kind of like counting. If you start with a natural number of objects, and if you add on another natural number, it's just like counting up, and you're always going to get a larger number, but that larger number will still be natural. It would be a number we could use to describe how many of something. Okay, how about subtraction? Okay, so examples like 6 minus 2, 4 minus 4, 3 minus 5. Well, fairly quickly, I think we can see from these examples, sometimes the answer is natural, but sometimes it's not. Okay, so 0 is not a natural number, and -2 is not a natural number. So the natural numbers are not closed under subtraction. It's possible to get an answer that's not natural. How about multiplication? 3 times 2, 12 times 120. 5 times 15. Okay, all of these give answers which are natural numbers. And inductively, take your best guess. It seems like these numbers are closed under multiplication, and that is true. Okay, and then finally division. 6 divided by 2. How about 12 divided by 5? Okay, so that one's 3. This one, let's see. I think that's 2.4. Okay, so we can get an answer which is a natural number, but it's possible to get an answer which is not, so the set is not closed under division. Okay, so yes, closed under multiplication and addition. No, not closed under the other two. All right, how about integers? So think about adding them together. And now we want to talk about natural numbers, 0, and all of the negatives. So we could do like -3 plus 12, 0 plus -5, etc., etc. Okay, all of those answers will give you another integer. So inductively, I think we can say yes, that set is closed under addition. All right, how about subtraction? Things like 5 minus -3, or -16 minus 4, or 8 minus 10. Okay, all of those give integer answers. So yes, that one's closed as well. Multiplication. 3 times -2, 5 times 5, 1 times -4. All integer answers. That one's closed too. And division. 5 divided by 5, 6 divided by 2. We could even do -6 divided by 2. Okay, those are integer answers. However, something like 5 divided by 4, not an integer. So it is possible to divide and not get integer answers. So not closed under division. Okay, now the next two, these are finite sets. The first two were infinite, and there's no way to really check all of the different combinations, so we had to just look at some examples and then make a conjecture to decide whether or not we think that that would be a true property for all numbers in those sets. Now the finite ones, we actually can prove deductively whether or not these sets are closed. And what we can do is make a little table to check all of the different combinations of those numbers under these operations. All right, so what you do is you list all of the elements at the top of the table, and then you list them down the side in the same order. Right. And you may remember seeing, multiplication tables or addition tables when you first learned these. So we're just doing the same thing here, it's just with a much smaller set than you're used to seeing. All right. And then in the top left corner, we put the operation that we're going to check. So let's check addition first. Now the left side, to do these in order, you start with this number first, and then to it you add the number along the top. All right, so for example, right here, I'll put the answer to -1 plus -1. Okay, and that's -2. Then here, this is -1 plus 1. All right, down here is 1 plus -1, and here is 1 plus 1. All right, now to decide if this is closed, once you've filled out the table, you just look at the answers in the middle, and you see if the answers belong to the original set or if you see anything that's different. So here actually none of the answers belong to the set, so this set is not closed under addition. Okay, now let's try the same thing, but let's try this for the other operations. So let's do multiplication next. Okay, so -1 times -1 is 1, -1 times 1, 1 times -1, and 1 times 1. Now in this example, all of these answers came from the original set, so this one is closed. We can say that this set is closed under multiplication. All right, and then we do the same thing, check subtraction and division. All right, so subtraction is, let's see, this. Okay, and that one is not closed. We have some answers that are not in the set. And finally, division. Okay, -1 divided by -1 is 1. This is -1, -1, and 1. This one is closed. Okay. All right, as an exercise, and I will leave this one for you to do and try on your own, but do the same thing for the set 0 and 1. So this is finite, so make yourself a little table, list the elements, and then try out each of the 4 operations in that top corner. So go through, and then for each of those decide whether or not you think the set is closed. Subtraction and division. Okay, yes or no? All right, usefulness of this property. So here are a couple different ways that we could use this. One is to decide without actually working out some of these operations whether or not we think the answer is correct. All right, now these problems we want to not talk about closure of the real numbers because it doesn't really tell us much. All right, for instance, 12 plus 14 is also a real number. Okay, that's true. All right, and a real number plus a real number is a real number. That looks pretty good too. All right, so instead let's look at maybe some different sets to decide whether or not this seems to be a correct answer. All right, so 12 and 14, how do we know that that's not 27 without actually doing the addition there? All right, well, one way is to know or to observe that 12 is an even number and 14 is an even number. And think about what you might have learned before. What happens when you add 2 even numbers? What kind of answer do you get? Well, you get another even answer. Right? So you may not have heard the word closure before, but you've probably learned this closure property, which is that the set of even integers, and I think we called this E before, the set E is closed under addition. Closed under addition. So when you add 2 even numbers, you get an even answer. All right, How about 50 plus 70? Well, what type of answer were you expecting to see? If you notice, these both end in zeros, and you may remember that your answer should also end in a 0. So what we just need to do is describe what set 50 and 70 belong to. Well, these are multiples of 10, that's why they end in 0. So we can say that the set of multiples of 10 is closed under addition. And if we have proved that property, then we can apply it in this situation to say that, well, no, 102 is not a correct answer to that equation, since that does not end in a 0. It's not a multiple of 10. Okay, we have some other properties to talk about, but I think we'll stop there, and I will save those for a new video.